So I know you're all very tired. I'll try to present all of this in 1 hour. So the idea is not to teach you machine learning, is to teach you how to approach a machine learning project, okay? So I thought that it would be more useful for you to start with a presentation on the basic concepts involving a machine learning project. And then we will go to the actual tutorial in Python. So if you don't have Anaconda, maybe you should install it if you want to follow the code that I'll provide. Or you can use Colab as well. You don't need to install anything. So I have to say that this will be probably very basic for those of you who already have some experience working with data science or programming. But this will be useful if you're not experienced, if you don't have any experience with programming. So, as you know, machine learning is to create models with tunable parameters that can be adapted to observed data and that can later be used to predict instances of new data. And at the most fundamental level, machine learning can be categorized into supervised and unsupervised learning. Well, I have to thank Matthew for showing me today that there is a third category, which is reinforcement learning. In this workshop, I'll focus on classification and clustering. So classification is when you want to create decision boundaries or identify decision boundaries to separate the labels in your data set. And clustering is when you don't have any label and you want to find structures in your data. You want the data to let the data speak for itself. So we will be focusing mainly on Kmeans, logistic regression, decision trees, and random forests. And we'll use a data set for the prediction of mortality using the MIMICIII data. So let's say that you already have your data set pre-processed. What you want to do is to divide your data into a training and a test set so that you can test your model using data that was not used to create the model. You also want, ideally, a validation set so that you can tune parameters, change the model architecture, select features, and so on. It's also important to choose a single number evaluation metrics such as accuracy so that you can have you can easily rank different algorithms according to one metric that you want to do well on. But in many applications, accuracy is not suitable because, for example, in the data set that I'll be showing, we have 13% of patients are non-survivors, which means that if we create a model that predicts everything as being a non-survivor, we have 87% accuracy, which is apparently a good number, but it doesn't mean anything because it predicts everything as a non-survivor. So you might want to look at other measures such as sensitivity and specificity, because you probably want a classifier with a lower accuracy but higher sensitivity to the class that you are interested in classifying. There are two big sources of errors in machine learning: bias and variance. So bias is the training, the error rate on your training set and is related with underfitting. And the variance is the difference between the error on the training set and the test set. So if you have a high training error and a validation error similar to the training error, you should suspect of high bias. And if you have a low training error and a very high validation error, you should suspect of high variance. Yeah, it's important to note that machine learning is not the same as curve fitting. You don't want to perfectly fit a curve to your data. You want to fit a curve that generalizes well enough to new data. So for example, here the random forest has created many decision boundaries that are very specific for small regions of space. So the variance is very high. The model is overfitting the training data. So as you can see, as you increase the complexity of your model, you also increase the variance. So when we're dealing with algorithms that use a fixed number of parameters, these are called parametric algorithms. And they are useful when you have few data, you want to easily interpret the results. For one common example is logistic regression. On the other hand, non-parametric algorithms, in non-parametric algorithms, the number of parameters can grow with respect to the sample size, and they are very useful when you don't want to make too many assumptions about the underlying function that you're trying to model. And you also don't want to worry too much about choosing the right features. So examples are the KNearest Neighbors and the decision trees that we'll see afterwards. So decision trees can be used for classification and regression. They give you a tree-like structure with a series of rules that you can follow in order to get to, in this case, to a classification. They already have embedded feature selection, which is an advantage of using this algorithm. They are simple to understand, to interpret, if they are small enough, of course. However, they can be very unstable, because if you change slightly your input training data, you can have a totally different decision tree. So in this case, it is better to use a random forest. It's a much more robust algorithm. So a forest is a large collection of trees. A random forest is a collection of random trees, where each tree is trained over randomly selected training samples, and also random features. So because each tree is trained over a different training set, they are said to be decorrelated. And actually with this, you can decrease the variance that you cannot do with a simple decision tree. So how can you deal with the bias variance problem? So if you have high avoidable bias, you can try to train your algorithm longer by running more iterations, or you can try a more complex model by, for example, adding more trees to your random forest. You can modify or add features, or decrease regularization, which is something that you do to decrease overfitting. On the other hand, if you have high variance, one thing you can try is to get more data. Of course, this is not always possible, but you can extract more variables for the, in this case, the cohort of patients that you already selected. You can try to decrease the number of features, try to add a regularization parameter, which can also have an impact on bias, of course. So you should always do this. You should always make several tests in order to get to a good model. So when you start a machine learning project, I think you should start with some idea of how to build the system, implement the idea in code, and carry out an experiment that tells you how well the idea worked. You use your validation set to do this, and then by the end of this, you repeat the process all over again, because it probably won't work at the first time. So it's hard to correctly guess the most promising directions, so don't start off by trying to design the perfect system. Start with a basic system. Choose well your validation and test sets, meaning that they should reflect the distribution of data that you want to do well on. And you can use error analysis to help you identify the most promising directions. So error analysis is when you go through some misclassification observations that you have and you try to understand what's happening. So we can start now with the actual workshop in Python. So as you know, Python has been gaining a lot of ground recently, and it's mainly because it provides these libraries that already have the reference for most of the operations that you will need to perform. So this is very useful. For example, if you are going to work with Python, you will definitely gonna use NumPy, which is the fundamental package for scientific computing. Pandas, that provides you easy to use data structures. Scikit-learn, which contains all the machine learning algorithms. Matplotlib and Seaborn for plotting your data. I use IPython as well for dynamic data visualization, and the Jupyter notebook. So don't worry about these two libraries. I only use them to plot the decision tree, but afterwards, if you want to do that, you can call me and I'll help you with that. So if you want to have access to the workshop, you can go to my GitHub account, which is in this link over here, and download the machine learning type A notebook. I'm going to show you the code here, but ideally you should run the workshop on your machine so that you can experiment the code on your own and see if you have any questions. So, do you guys have access to the tutorial? You can ask questions if you want during the presentation or afterwards if you want. So, yeah, this is a bit small. Okay, so the idea is not to go into the mathematical theory, but rather to provide you the basic intuitions of the algorithms. And most of all, I'll start by going through the data pre-processing and data exploration steps, which take most of the time. So you can't start by just building or training a model. You don't want to put garbage into your model, right? So you really need to understand the data that you are working with so that you can understand the results. So data exploration and pre-processing are very important. So I extracted pre-processed data set from MIMICIII, which is provided in this link over here. So someone extracted some vital signs and some scores and mortality information for the first 2 days in the ICU. And that's where we are going to start, because it's a simple data set, so I can show you some basic steps. So the first thing I'm going to do is to import the libraries that we need for data exploration. I'm going to ignore some warnings. For now, I don't use this. The data set, if you want to download it, you should use this second line of code, which is downloading the data set from the Dropbox. Okay. And using the data.head, we can, oh, sorry. Okay, so using the read CSV function from pandas, you can give the path to your CSV file with the data, and it will import it into a pandas data frame. Here I'm saying that I want the ICU stay ID to be the index column of the data frames, so that this way it will be easier to perform some operations afterwards. So if you do that data.head, you see the top 5 rows of the data set. And you can see that we have several observations collected at different times. We have diastolic blood pressure, Glasgow Coma Scale, glucose, heart rate, mean blood pressure, and so on. We have age, gender, pH, and our outcome, which is mortality. And you can already see that a lot of data is missing. So we don't have records at, oops. So for example, after 0.066 hours in the ICU, we don't have records for all the variables, which is expectable. So this cell is only printing the number of ICU stays, number of survivors and non-survivors, the percentage of mortality. And then using the info function and the describe function, we can get some summary statistics on the data sets. So with the info function, we can see how much information is missing for each variable. So we have 21,000 ICU stays and more than 1 million observations. So, but what I really want is to know the missing data at the patient level, right? So I can do that by using the group by function to group my observations at the level of the patient. So I'll group them by ICU stay and use the mean operator. And then I can see how many patients have missing information for every variable. And I decided that I don't want to use height nor weight, because I would have to discard a lot of patients who don't have this information. This decision is up to you. So in this script, I'm using a Seaborn function. Seaborn is a package for plotting. And I'm going to use the box plot to identify outliers, okay? And you can't even see the box plots because the data has so many outliers that you cannot see the mean or the maximum values. So there, you know that there are several ways to deal with outliers. You can use statistic methods to automatically identify them and exclude them or modify them. What I decided to do was to create some rules based on expert knowledge to say, okay, so it's very unlikely that the systolic blood pressure is above, no, this is not a good example actually, but it's highly unlikely that the pH is below 6.8. I think it's even impossible, but you doctors should know better. So I created this set of rules and excluded all the data that is outside these boundaries, okay? And now if we plot the data again, and with Seaborn you can create really nice graphs. So if you use the strip plot, besides the box plot, you can plot all the points in your data sets. And now you can, and if you use also the your outcome as your x axis, then you can see the box plots by outcome, which is really cool. So as you remember, we have many observations in time. So in order to compare the observations, it's more useful to aggregate them by hour. So if you use the group by function and you aggregate the data by ICU stay and hour, and you use the median value, then you get a nicer data sets because you have 1 point for 48 hours, okay? So if you plot that, this is the data for 1 ICU stay. So all the vital signs are shown here. We have data from time 0 to time 48. And some points are missing, but this is not a problem because we won't be using the complete time series. We will extract some relevant features later on. But before we do that, it's advisable to select a minimum number of features for every variable. So I decided to choose 2 features, 2 observations, I'm sorry. So another type of graph that you can use in exploratory analysis is the pairwise plotting, where you plot every 2-dimensional relationships that you have in data. This usually doesn't tell you much, but it's a nice test on data integrity. So you can see, for example, that fever is correlated with tachycardia. You don't see many clusters here because we are dealing with mortality and it's not an easy problem. So if you found clusters here, it would be unexpected. It's easier to find clusters if you look at time series, at the complete time series, and here I'm plotting the average signal partition by survivors and non-survivors. And there are clear trends, right? So for example, Glasgow Coma Scale is decreasing for the non-survival group and increasing drastically for the survival group. So what this data exploration tells us is that the time series contain valuable information. But if we were to use the complete time series, we would have more than 500 features. So if we have 48 points for 11 variables, we have a huge feature set. So in this case, I decided to extract some relevant features from the time series. I used the maximum, minimum, standard deviation, and mean value. You can use several others, for example, the time between the maximum and the minimum, or the time until the maximum, or the difference between the last one and the first one. It's up to you. And you can easily obtain that with a group by function. You just have to group by your ICU stay and apply the operators that you want, and then you aggregate everything. So our feature set now contains all of these features, but it's actually smaller than before, right? So as I was saying, you should divide your data into training and test sets. I'm using the train test split from the scikit-learn library. You can also do cross-validation. It's even better, which is when you divide your data into k folds and you use every fold to test and train the data. So you just need to provide the input data the output data, and the size of your test set, which I decided to be 20%. I also decided to force us balancing of the data, because we have much more patients from the non-survival group, our class 0, the survival group, I'm sorry. I decided to randomly eliminate some of them, to exclude them from the training sets. So another thing you can do is to add more patients from your class of interests, from the non-survival group, which is the class you want to predict. Which is, I think it's actually better to force oversampling than an undersampling, because when you do undersampling, you are losing information. And if you do oversampling, you're not losing anything. You're just making copies of the class of interest, okay? So the K-means clustering, which is known as an unsupervised learning method, is nothing more than calculating distances between observations. So what the algorithm is doing is randomly creating centers in the feature space, and then assigning observations to each center, and then updating the cluster centers to reflect the mean value of the observations that were attributed to the centers. It's very easy, and I'm going to show you how it works in this 2D database, 2D data sets for mean blood pressure and mean heart rate. If you want to use the scikit-learn function, you need to import the cluster package, transform your data into a matrix, and then call the function Kmeans. Tell the function how many clusters you want. Choose a random state so that you can replicate your results afterwards. If you don't choose a random state, your results will be different if you run the algorithm several times, because it has some randomness to it. Okay. So this is the easy way. But if you want to use your own code, you can see here that it's very easy to implement K-means with a few lines of code, right? And you can easily understand how it works if you implement your own version, or if you look at this one. One problem with K-means is that you have to provide the number of clusters. And it will always find clusters in data, even if they are not there, or even if they don't make any sense. So for example, if I say that I want 20 clusters, it will create the 20 clusters. But do you think they make any sense? Probably not, right? So we saw before that 2D data doesn't show any patterns, but we also saw that the time series were very different between survivors and non-survivors. So let's have a look at clustering using the time series. I'm choosing the Glasgow Coma scale to illustrate, and using 5 clusters, this is what we get. So these are the cluster centers. This is the distribution of mortality in the cluster centers. And this is the data around each center. Okay, so we didn't provide the mortality to the clustering, but even though we didn't do it, we can still find differences in terms of mortality. So for example, the pattern in blue, which is the one where patients have decreasing Glasgow Coma Scale since admission until the end of the stay, is associated with a very high mortality, which makes sense, right? Because Glasgow Coma Scale is deteriorating. And when Glasgow Coma Scale is improving with time, the mortality is very low, which is this cluster number 4. So if you want to perform clustering of time series, I advise you to normalize the data before so that you can compare evolution in time and not the magnitude of the signal. So I've done it for all the other variables and selected the number of clusters. This is not important. So now, before starting the machine learning part, I'm going to normalize all the data between 0 and 1. You can use the preprocessing min-max scaler to do that. And all your features will be transformed, so that features that are within a higher range don't have more influence in the determination of parameters. That's the only reason. You don't need to do this for decision trees or random forests. I'm also going to add another layer of information to the extracted features. So the cluster centers will be used as input data. So the label to which each observation or each patient belongs is used as information to predict mortality. So it's another type of feature, and it's a way to incorporate your clustering analysis into the prediction models. So if you are familiar with the area under the ROC curve and the ROC curve, it's also very easy to get those in Python. You just have to import the scikit-learn metrics package, use the ROC curve to get your false positive rates and true positive rates, and then using those values you can calculate the AUC using the AUC function. I usually optimize the thresholds so that it doesn't have to be 0.5. It can be an optimized value so that you can control your sensitivity and specificity. Logistic regression can be easily implemented using the linear model from scikit-learn. There are other libraries that provide logistic regression, but I'm using this one because it automatically performs regularization. And I'm going to show you, this code is used to perform sequential forward selection, which is when you sequentially add features to your data set until you don't see any improvement in the performance. So what I'm doing here is the first color shows a univariable analysis, which is when you test only one feature. And then you keep on adding features until there is no improvement in the performance. And this way you can reduce the size of your feature set, right? But there is no implementation in Python to do this. That's why you see this big chunk of code here, okay? There is an alternative which is for recursive feature elimination, which is similar, but we start with all the features and we sequentially exclude some from the set. And you can do that using the feature selection package from scikit-learn. With 2 lines of code, you can select a feature set. But in this case, the features will be selected based on the value of the coefficients of the model, okay? So I was telling you that you should have a single evaluation metric, but actually I usually like to look at sensitivity, specificity, and AUC, and also at the ROC curve. This is the result from the training set, and this is the result from the test set using logistic regression. So another simple algorithm that you can try is the KNearest Neighbors, which is known as a lazy algorithm because it doesn't do anything during the training phase. It just stores information, and then when you have to test some new points, it basically goes through all your training data and compares every observation to it. And the observation that is closer to your test observation is the one that gives the prediction. But of course, you can select the number of neighbors. So if you have 3 nearest neighbors, you're saying that you want your new observation to be the average of the 3 closest, or the majority voting of the 3 closest observations. And you can do that using the KNearest Neighbors classifier. You just have to provide the number of neighbors. And if you want some observations to have more impact on your classification, you can use the weights parameter. This algorithm usually performs bad. You can see it here. The sensitivity is only 0.56. Now let's see the performance using a decision tree. The decision tree in Python uses the CART algorithm, and I'm going to use the Gini index function, which I'm not going to explain, but you can. There's a very simple explanation here. It basically provides an indication of how pure the leaf nodes are. Okay. There are some important parameters that you should select when using decision trees. The criterion you want to use to measure the quality of the split, the maximum number of features that you want in each tree, the maximum depth, which represents the complexity of the tree, the minimum samples per split, the minimum samples in the leaf nodes, and the random state as well if you want to have reproducibility. So I'm creating a decision tree with a maximum depth of 5 with at least 20 samples in each leaf. And I get a sensitivity of 0.82 and specificity of 0.77 in the training set. The performance in the test set is somewhat lower, which is expected, but this can be improved. You can visualize the tree. It's useful, but it's not that simple to interpret because it's a big tree, right? You don't want to look at all these rules. You can also compute the feature importance, which will give you the relative importance of each feature in the decision that you are making. Now, the random forest follows exactly the same procedure, but instead of 1 tree, you can have, here we'll have 100 trees. And yeah, if I use 100 trees, this is the performance I get on my training set. Yeah, 100%. This is clearly overfitting the training data, because when I look at the test set, the performance is much lower. So we have to decrease the complexity of the random forests. We cannot have that many trees, or we should decrease the depth. Something has to be done to reduce the overfitting. So if I reduce the depth, yeah, the overfitting reduces a little bit. Let me try with 10. Yeah, it's even better. Similarly to the decision tree, you also have the feature importance. So we are getting to the end of it. I mean, there are several other algorithms that you can try with scikit-learn. So as you've seen, you just need to use one function and understand what the algorithm is doing so that you make sure that you can interpret the results. And one thing that I didn't do was to change the parameters of the models, which is something that you want to do if you want to improve the performance. So you should iterate over a range of parameters and then choose the best one using your validation set. And then you can test that best one using a test set, not used before, okay? Here I just showed you some examples using a fixed set of parameters. This is the difference in the performance obtained in the training and the test sets. It's very high in the first random forest that we created because it was overfitting the data, right? So yeah, I didn't go into much detail, but if later on you decide to use this and you have some questions, please let me know that I can go to the groups and help you, okay? And if you have any questions now, feel free to ask. So how many of you have experience with Python? I could tell. Okay, not so many. And do you think that you can start using Python now if you have data? Yeah, okay. So thank you for listening, and